Welcome to this lecture. In the last lecture, we are trying to do some numerical analysis to identify the inversions that are suffered by different tasks and the duration for which the inversions occur. For an example problem, we had done the analysis for direct inversion. Now, let us continue from there. We will consider the same problem and we will now try to identify the inheritance related inversion and the duration, and we will represent in the form of a table. This is the same problem that we were considering in the last lecture, and now we are trying to identify the inheritance related inversion. T1 and T2 will not cause any inversion to the lower priority tasks, because they are of already higher priority, and high priority task does not cause inversions. It is the low priority tasks which cause inversions to the higher priority task. Now, let us see whether T4, let us look at the resource R2 here, and T4 is using the resource, and then T1 is waiting for the resource. In that case, the priority of T4 will get enhanced to be equal to T1, and now the tasks which are of higher priority T2 and T3 can undergo inheritance inversion, but what will be the duration for which they will undergo inversions? T2 and T3, they will undergo inversion for 5 units time, that is the uses of T4 of the resource R2. But what about the resource R3? When T6 is using the resource R3 and T2 is waiting for the resource, T3, T4, T5 will be prevented from using the CPU, because T6 is executing with a high priority, that is the priority of T2. And what will be the duration for which T3, T4 and T5 will undergo the inheritance related inversion? So, that is equal to 8. So, all the three of them will undergo 8 units at most inversion on account of T6 using the resource R3, and that we have represented here, that T3, T4 and T5 can undergo 8 units of inversion on account of T6, and T2 and T3 can undergo 5 units of inversion on account of T4 using the resource R2. Now, let us do the analysis for avoidance related inversion for the same example problem. So, this is the problem. Now, let us identify the the avoidance related inversion. Now, let us see whether T1 and T2 will cause an avoidance related inversion. No, because these are of lower priority tasks, and high priority tasks do not cause inversion to lower priority task. It is the low priority tasks which cause inversion to high priority task. Now, let us see on account of resource R2. Let us say T4 is using the resource R2, then the current system ceiling will be set equal to the priority of the task 1, T1, and in that situation T2 will not be allowed access to any of the resource that it needs. So, to what extent, to what duration it can suffer avoidance inversion. So, that is 5, that is equal to the resource uses of T 4 for R 2, and even T 1 can suffer inversion when it requests resource R 1, because its priority is not greater than the ceiling priority. Now, what about R 3? When T 6 sets it uses the resource R 3, the CSC is set equal to the priority of T 2, and in that case, if T 4 is trying to use the resource R 2, it will be prevented, and the maximum duration for which it can undergo inversion is 8 units. And similarly, T 2 will not be allowed to use a resource R 1, because its priority is not greater than the ceiling priority of R 3. So, we can represent that in the form of a table. On account of T 4 using R 2, T 1 and T 2 undergo 5 units of inversion. On account of T 6 using resource R 3, T 4 and T 2 undergo inversion, T 3 and T 6, T 3 and T 5 do not go inverse avoidance related inversion, because they do not use any resource. If we look at the tables that we developed, they are always in the form of a upper triangular matrix. So, all the values are in the upper triangle. Why is it so? Can you think of any reason? Okay, the answer is that a task does not suffer any inversion due to higher priority tasks. If a higher priority task is using a resource, the lower priority tasks need to wait. That is not an inversion. The inversion occurs when a low priority task is using resource and high priority task is waiting. So, it is not really symmetrical. The inversion occur in one way when the low priority task is using resource and high priority task is waiting, and not the other way around, and therefore, it is a upper triangular matrix. Now, let us identify what is the maximum duration for inversion that a task may undergo, considering all types of inversion. The first thing to note is that a task can suffer at best only one of the inversions, either direct, inheritance or avoidance related inversion. It cannot suffer multiple inversions of this type. Once we agree to this result, that a task can suffer at most one of the inversions, then to determine the maximum inversion that a task can undergo, we need to look at the 3 tables that we developed, and then look at the maximum value of the entry corresponding to that task in the 3 tables, and that is the maximum duration for which it can undergo inversion. There are some practice problems. You can please practice some problems where maybe you can construct 5 tasks or 7 tasks, 2 resources, or maybe 4 resources, 3 resources, and so on, and please try to work out some examples in the analysis of the inversions that different tasks can undergo. Now, even if we know what is the maximum duration for which a task can undergo inversion, how do we check the schedulability? Please remember that in the rate monotonic scheduler, we are using the Liu and Lehoczky result to determine the schedulability, and for each task we were using the execution time of the task and the time for which the all higher priority tasks need to use the resource in the form of such an expression, and then checking whether it is less than equal to the deadline or the period of the task. Okay, deadline is equal to the period. Now, when the tasks share resources, we need to just add this term here B I, and B I is the total blocking time for a resource on account of the lower priority tasks. So, once we develop the 3 tables for 3 different types of inversion, when priority ceiling protocol is used, we determine the highest entry corresponding to that task and use that value here, and then determine whether the task set can be schedulable. Now, can the priority ceiling protocol be used in the dynamic priority systems? For example, the earliest deadline first scheduler. Can we use a resource sharing protocol with EDF? In the dynamic priority systems, the priorities of the tasks keep on changing with time. Depending on how close they are to the deadline, the priority keeps increasing. But if you look at the protocols that we considered for resource sharing, we assign ceiling priority based on the priorities of the tasks that use that resource, and if the priorities of the tasks keep on changing, then we have to keep on recomputing the ceiling priorities. Each time the priority of a task changes, we need to change the current system ceiling, need to change the ceilings associated with the resources, and this can be too much of overhead, because there can be many instances. Frequently the priorities of tasks will change, and each time we need to do this, that the current system ceiling, the ceilings associated with resources and so on we need to change, and therefore, if you are using a dynamic priority scheduling algorithm, it becomes very difficult to have any resource sharing protocol to be used in that situation. And therefore, if you analyze all real time applications where the tasks are non-trivial, they share resources with each other, then it is invariably the rate monotonic scheduler or small variation of that is used. Now, let us compare these 3 protocols that we looked at, because all the 3 protocols are used in some application or other depending on their advantages. So, let us just recapitulate their advantages and disadvantages. The simplest protocol was the priority inheritance protocol. If you are using a very small application, a small embedded system which hardly has a operating system, then the priority inheritance protocol is the one to use. It requires very little support from the operating system. It overcomes the unbounded priority inversion, but then it suffers from chain blocking and deadlocks, and we need to program carefully so that chain blocking and deadlocks will not arise. So, the priority inheritance protocol is used for small applications. But what about the highest locker protocol? It requires moderate support from the operating system, solves the chain blocking and deadlock problem, but then it introduces a new problem, that is blocking by the intermediate priority tasks. They suffer inheritance related inversion, and that can be substantial. The priority ceiling protocol overcame most of the problem of the basic inheritance protocol and the highest locker protocol. It is free from deadlock and chain blocking, and in contrast to the highest locker protocol, the inheritance related inversions are really low here. The main reason is that the priority of a task on acquiring a resource does not change until a higher priority task requests the resource. Now, with that discussion, let us conclude our discussions on resource sharing among tasks, real time tasks. Let us now start discussing about multiprocessor scheduling, because nowadays the multiprocessors have become commonplace. Even small embedded applications, they use multiprocessor, and invariably all desktops, all servers, laptop, handheld devices, etc., all use multiprocessors. But the results that we have so far seen are for uniprocessor. Let us see how those results can be extended for use in a multiprocessor situation. But multiprocessor scheduling is a much more difficult problem than the single processor. In the words of Liu, who is worked considerably in the area of scheduling real time tasks, the Liu-Lehoczky, Liu-Leland algorithms are all due to him. In his words, the simple fact that a task can use only one processor, even when there are several processors which are free at the same time, adds a surprising amount of difficulty to the scheduling of multiple processors. Now, let us see what are the difficulties, and we will look at some simple algorithm. We will not spend too much time here, because this is a large topic, but we will not really discuss in depth. We will just look at some simple strategies for scheduling on multiprocessors. Most of the results here have been obtained in the last 30 years, and most of the real time multiprocessor scheduling problems are NP hard problems, and therefore, simple optimal solutions do not exist. There are very few optimal results, mostly heuristic approaches are used, and also we use a simplified task models. If we look at the multiprocessor scheduling problem, then there are actually two sub problems. One is task assignment problem, the other is the scheduling problem. In the assignment problem, we first decide which task will run on which processor, and then how or what time will it run. So, there are two sub problem. One is which task will run on which processor, the second is how it will run, the scheduling algorithm. So, the task assignment problem is how to assign the task to the processor, the scheduling problem is how to schedule the task on the processor to which it has been assigned. But as we already indicated that optimal schedulers for multiprocessors are not there, because these are all NP hard problems. But then what are the optimal schedulers for uniprocessors? We have already seen this, that for static priority systems, rate monotonic schedulers are the optimal schedulers. In a dynamic priority situation, the earliest deadline first is the optimal scheduler. But then what are the complexities of these schedulers, the rate monotonic scheduler at EDF? If you look at the implementation aspects that we are considering, it is linear for rate monotonic schedulers, because if you remember, it said that there are fixed priorities, and then the implementation that we had, we could run the scheduler in one in O(n) priority. So, the linear for are rate monotonic and log n for EDF, and even rate monotonic we have more efficient scheduler O(1) scheduler, that also we had discussed. But the general real time scheduling of multiprocessor distributed systems is a NP hard problem. Now, let us look at some task assignment algorithms, and then we will see the scheduling algorithms, because the multiprocessor scheduling consists of two things: the task assignment and also the task scheduling once they have been assigned to a processor. So, let us look at the task assignment algorithm. There are some static assignments. So, here the tasks are assigned statically to a processor, they execute only on that processor once we have assigned. Whereas, we also have dynamic algorithms where a task can migrate from one processor to other, and at different time instants it can execute on different processors. Naturally, the static ones are simple and more efficient, and few examples are the utilization balancing algorithm, next fit algorithm for RMA, bin packing algorithm for EDF. Whereas, for dynamic priority we have the focused addressing and bidding algorithm and the body algorithm. We do not have time to look at all these algorithms, even though in the textbook these are given. We will just look one of the algorithm to get a flavor of the task assignment algorithm. We will look only at the utilization balancing algorithm. Here the tasks are maintained in a queue, and these are arranged in the increasing order of their utilization. We take out one task from the queue at a time and check which is the processor that is currently the most underutilized processor. We assign it to that. So, basically a greedy algorithm. We look at the one which is currently the least utilized and then assign the task to that, and finally, we will see that the utilization of the individual processors after the algorithm completes assignment is not really equal to the mean utilization, or in other words, the utilization is not really fully balanced by using this greedy algorithm. And the utilization balancing algorithm is used in the conjunction of EDF. The allocation is done by the utilization balancing algorithm, but the individual processor scheduling is done by the EDF algorithm. Can you think of any reason why EDF is used, not the rate monotonic scheduler? The answer is that in the EDF the utilization of the processor can be up to 1, whereas in the rate monotonic we have seen how many the utilization depends on how many tasks are assigned to the processor and so on, that we have not considered in our utilization balancing algorithm, and therefore, it is the EDF that is used along with the utilization balancing algorithms. We will not really look into the other algorithms, because this is a short course of only 10 hours. Now, we will look at few more basic issues in real time operating systems. So far, we have been looking at a very central issue of all real time operating systems, that is task scheduling. Now, let us look at some issues for real time operating systems. Can we distinguish a real time operating system from a traditional operating system, or to state in other words, can we identify how does a real time operating system differ from a traditional operating system? What are the points that we need to consider to check and say that whether an operating system is a can be used for real time application, or is it traditional non real time operating system. The issues that we need to consider are support for real time priority levels. We have seen that the real time scheduler, especially the rate monotonic algorithm, there once we assign priorities to the tasks during design time, the priority should not change. This is also called as static priority level or real time priority level. As you will see in our next lecture, that the traditional operating systems, they keep on changing task priorities. Every time the task is run, its priority is recalculated and new priority values are assigned. So, those are not really static priority levels. A real time operating system must have support for static priority level. Once the designer assigns a priority to a task, it should remain fixed to that priority level. The second is real time task scheduling policy. The operating system should support some real time task scheduling policy like the rate monotonic scheduler. And this scheduling policy is a central requirement for all real time operating systems that we had seen. Support for resource sharing protocols. Protocols such as priority ceiling protocol or at least the basic inheritance scheme should be supported by the operating system to be able to develop any non-trivial real time application. Also, the preemption time of tasks should be of the order of microseconds or maybe milliseconds, but it cannot be, should not be seconds, because in any real time application the response time itself is only few milliseconds. But if you look at the traditional operating systems such as the Unix, the preemption time is of the order of a second, and also we have interrupt latency requirements. The latency should be small, that is, when interrupt occurs to the time the interrupt is processed, the time should be small. There are additional requirements like memory locking support, that once a task uses certain memory, there should not be swapped to the hard disk and so on. It should be locked to the memory. Support for timers, because timers are very crucial in real time applications, both the periodic timer and the aperiodic timers. Support for real time file support. Real time file systems should be supported, and these issues we will elaborate in the next lecture, and the device interfacing facilities, because in many of these real time applications we need to work with different types of peripheral devices. With this we will stop here, where at the end of the lecture, and we will elaborate these issues in the next lecture. Thank you.